Welcome to TinyML and Efficient Deep Learning Computing 2024. I'm Professor Song Han. Very glad to teach this class again. This is the third time we offer this class. We're going to learn efficient deep learning computing, how to make neural networks run faster, train with faster, and inference faster. Remember 2 years ago when we first opened this course, only 30 students. Last year it was 90. This year is more than 200. So welcome all. I'm very glad to have you all here. And hopefully we'll have a very fruitful semester altogether. So this is a brief introduction of myself. I graduated from Tsinghua University and got my PhD from Stanford with Professor Bill Daddy. I worked on model compression and efficient deep learning computing during my PhD. Published a deep compression paper, which set the foundation for modern neural network acceleration and compression, and published a paper called the Efficient Inference Engine, which is actually a top 5 cited paper in 50 years of ISCA. During my PhD, I co-founded a startup called DeFi Tech for efficient AI chip, which was later acquired by Xilinx, and later Xilinx is acquired by AMD. That's a very popular story in Silicon Valley. So in this course, I will teach some of the how to make sure the research is very fundamental, not only fundamental, but also practical. So I joined MIT about 6 years ago, very exciting journey. We've been working on from TinyML to large language model, acceleration and compression. One of the most exciting paper we did in the past few years is the AWQ for large language model quantization, which got the best paper award at MLSys. And also it's having already more than 6 million downloads in Hugging Face. So if you want to deploy a large language model, make it 4 times smaller, then AWQ is the technique to go. And we will learn that in this lecture. You're going to implement that, not only implement that, but also deploy a large language model locally on your laptop, which will be pretty exciting. So at MIT, I also co-founded a startup called OmniML, working on efficient deep learning computing, model optimizations. So in this lecture, we'll learn all the secret sauces from those two startups. So those 5 homework will be very, very helpful if you learn them, master them all. So we very carefully curated 5 assignments, five homeworks. They're all hands-on homeworks. So we try to, for you guys, use the minimum effort to learn the most amount of knowledge, the best to utilize your time. So please do those homework very well. Yeah, we'll have 5 labs, and each TA will be responsible for one of them. And we have office hours every Tuesday and Thursday, and feel free to come to our office and can help you with any questions you may have. Okay, let's start by motivating why do we need efficient deep learning computing. So let's see the supply and demand for AI computing. So in this chart shows throughout different years, the model size of large language model in red versus the GPU memory in green. We can see the large language model size grow from 0.05 billion parameters, the initial transformer in 2017, 2018, to about 1.5 billion parameter in GPT-2, roughly in 2019, 2020. And recently, there's even trillion parameter models being trained in the world, right? It's growing super fast, even much faster than the amount of GPU memories that is available in a single GPU, right, which is showing green. So this big gap, the gap is getting larger, actually, with recent years. And if you see the supply and demand curve, that is driving up the price, right? Making deep learning super expensive to train, super expensive to serve, right? So we are going to learn techniques to bridge the gap using efficient model compression techniques so that we can improve the utilization of the hardware and also reduce the model's size, memory requirement, computation requirement to bridge this gap. So rather than train a model and directly run inference on the top, we now can train a model, compress it before deploying the compressed model for inference. So in recent years, the amount of publications in model compression and acceleration on compressed sparse model is getting a lot faster. Number of publications is increasing very fast in recent years, and we are going to learn these techniques. How do we utilize compression and sparsity to accelerate neural network inference? So in this lecture, we are going to start with three sections, from vision to language to multiple modalities, to understand the computation demand of this AI workload and see where we are among the frontier. So let's start with vision tasks. So talking about computer vision, we have to mention ImageNet and also AlexNet, right? So AlexNet, this is actually the ImageNet error rate, which is decreasing across the years. And if you can see carefully, in 2012, that's the year where we have the biggest improvement. That is actually the year when I started my PhD at Stanford, where AlexNet just came and just so amazingly blown away a lot of the traditional techniques. And later throughout the years, the accuracy is just decreasing and decreasing, even surpassing the human performance, which is the last bar. So it is really the big data and compute and algorithms that is driving up the performance of these workloads. But that is no free lunch. As we can see in this figure, the x-axis is the max, the amount of computation. We are going to learn what is a max in detail in the next lecture. And the y-axis is the accuracy. We can see a trend. The higher accuracy you want, actually the larger the amount of compute that needs to be to run the inference, right? And the larger the circle means the larger the model size, which means the accuracy doesn't come as a free lunch, but you need through a lot of memory, a lot of compute to achieve such memory, such accuracy. And what we are going to learn in this lecture is to push the frontier, okay, to reduce the amount of computation, but doesn't sacrifice the accuracy or even increase the accuracy. Right? We can drastically reduce the amount of max, okay, to the left corner, and then maintain even higher accuracy by neural architecture search techniques, which we are going to learn in a few months. And such amazing efficient AI techniques enable running these deep neural nets locally on the edge. For example, running on the phone, we can tag our photos. For example, summer, the trips, dining in different locations, different lakes, cliffs, geysers, right? And also can do people recognition locally on the phone. On the right-hand side is our from our lab to do on-device pose estimation. Everything is running locally. You don't have to worry about your data get transmitted to the cloud. And we are going to learn those techniques. Not only on mobile phones, but we can even shrink the model such that we can deploy them on IoT devices, even smaller microcontrollers. That is only a couple of dollars. They are much smaller, much cheaper, but in the meantime, it's more challenging because we have to make sure the model is small enough so that it can fit a microcontroller. And the inference library is efficient enough so that it can run different workload, not only classification, but also detection, like face and mask detection and person detection. And this project was done during COVID, so we're showing this demo using a microcontroller with only 256 kilobyte of memory. We can detect faces with a mask or without a mask. Not only on-device inference, but also we are going to teach on-device training. So AI systems need to continuously adapt to new data collected from the sensors, okay? We want to process this new data locally on device so that we can have better privacy, lower the cost, enable customization, and also enable lifelong learning, okay? But training is much more expensive than inference. And why is that? We have to store those intermediate activations. We have to calculate the gradient. We have to do the back propagation, etc. Right? So it's even harder to fit for edge hardware. In this lecture, we are going to also learn those on-device training techniques that can drastically reduce the amount of memory. For example, in this project called on-device training under 256 kilobyte of memory published 2 years ago, we can reduce the training cost from a few hundred megabytes to only 141 kilobyte. That's 3 orders of magnitude saving by using quantization aware scaling, sparse update, and tiny training engine. And we are going to dive deeper into such topic in about 2 months. And with that technique, we can have a demo here of on-device training under 256 kilobytes of memory. It's running on the OpenME CAM microcontroller. Right here, we attached 2 buttons with it to input the class. Okay, we have a green class indicating there's no person. We have a red class, red button indicating there is person. So initially, the model didn't have any training for these 2 classes, so it's the classification result is wrong. You can see the top right corner. See, there's a red or green showing on the top right corner of the screen. Before training, it cannot recognize distinguish person versus no person. And then we apply on-device training to press the button, green for no person, red for person, to manually input a few labels. And the back propagation is done locally on the device. And we have to do a couple of iterations. And then let's see the classification result. No person in red, no person in green, and classify them perfectly. And there's no Wi-Fi, there's no internet, everything just done locally on this microcontroller. Question here.
Is the data, like, is the image repeated?
Image what? Repeated?
After the training, it repeats the first image. So it would essentially be like, you can tell it was.
And that's why we are showing later using a real world setting. In the real world setting, we're showing it's not overfitting. Promptable image segmentation, right? So let's talk about another interesting stuff, segment anything, right? So this is a demo from Meta, where you can have a prompt dot, and then you can segment whatever you're looking at. For example, here, looking at a person, and the person will be segmented. But this is very computationally heavy. Previously, people store those features, extract the features, store them offline, and then only run the head on the browser. But one technique we'll introduce in this lecture, EfficientML.ai, can actually improve the throughput by 48 times. That's more than an order of magnitude faster with even higher accuracy on this chart. 48 times speed up on A100 GPU. So here is showing before the acceleration and after the acceleration. So before the acceleration on the first row, the model is running at only 11 images per second. And after using EfficientML.ai SAM, we can accelerate it to 182 images per second. So zero hardware investment, just using existing hardware, but making the model much more efficient. We can make the quality match exactly with the baseline model, but make it run a lot faster. And this is done by Zhou Yang, who made this project even before joining MIT, which is a pretty amazing project. So far we introduced the discriminative models. So as the algorithm advancement, people design these generative models that can not only recognize images, but also generate new images, right? So these are several examples like teddy bears, a bowl of soup, a photo of an astronaut riding a horse on the Mars. So diffusion models can create realistic images from natural language description, and we are going to learn how diffusion models work. So in order to accelerate it, we want to first understand how diffusion model works. But such amazing property comes at a very heavy computational cost. So the training stable diffusion cost $600,000 with 256 A100s, 150K GPU hours, which is pretty expensive. And this is a figure generated by Muyang, showing that this image or video generation model is actually much more expensive, like 3 times more expensive, just running a single step of the diffusion model on a 1K to generate a 1K by 1K image. Not to mention the videos, which is the red bar, 5.6 billion parameter model to generate a video, not even 1K, but it's just 480 by 720, generate 49 frames, just a few seconds with a single diffusion step. It takes 9 times more flops. So it's very expensive to run these image or video generation models. Okay. And also, as the resolution grows, the amount of compute also grows quadratically with the resolution. So that's a big problem we want to solve. We did a couple of projects we're going to introduce in this lecture, such as the GAN compression. We can reduce the computation by 21 to 9 times. And this is before compression and after compression, turning a horse into a zebra. Previously, it's running about 12 frames per second. Now it can run 40 frames per second. We're going to introduce techniques to achieve that. And also using this any cost GAN technique. For example, previously we want to do photo editing. For example, make the lady smile. It takes quite a while. Or make her look younger. We can just turn the sliding bar to the right by first projecting the image to the hidden space. It takes quite a while. What we did, and we're going to introduce, is first to train this once-for-all network, just a super network that contains many different subnetworks. So during the editing phase, we can use a smaller subnetwork running at low cost for fast prototyping. And finally, when we are satisfied with the result, we can run the large subnetwork only once. And as a result, you can see you can make her smile almost instantly. Or make her look younger. We can slide the second bar to the right, change the hair color. It's almost instant. Okay, by running this, using this once-for-all technique, we can derive many different subnetworks very quickly. Okay, and using this once-for-all technique, we can reduce the computation showing this yellow bar from 100%, 78%, 50%, 30%, even 19%. But you can hardly tell the quality. Hopefully, the quality is still well maintained, despite that we are reducing the max by up to 5 times. This is another technique we are going to introduce later in the later part of this lecture to accelerate image generation when we are doing the photo editing. So here we are doing image inpainting. So what is inpainting and outpainting? Inpainting is basically saying that we have a part of the image, say the black part in the rectangle. We want to add a horse to that, photograph of a horse on the grassland. And initially, stable diffusion takes like 1,855 max, costing 369 milliseconds. And after the compression acceleration, we can make it run at only 514 gigamax at 95 milliseconds. Similar on the right-hand side, to generate add a coconut tree to the image, we can accelerate it by 4.8 times. Since previous methods, you need to generate all the pixels, even though you're only editing a part of that. But with the Sage method, we can do sparse update, only update where you're only update the pixels, only generate the pixels that needs to be updated, and the remaining pixels remains the same. We are also going to introduce how to accelerate image generation by parallel processing. So with 4 GPUs, okay, can we generate even larger images even faster? Originally with 1 GPU, it takes about 12 seconds, right? A natural thought would be, if we have 4 GPUs, can we use like 3 seconds, 4 times faster? Unfortunately, naively doing this will introduce the artifact with duplication. using 4 GPUs, it actually generated 4 distinct images. The reason is that these 4 GPUs didn't communicate with each other. And as a result, they each generated an independent image. But communication will lead to the networking latency, right? And the way we deal with that is to overlap the computation with the networking such that we can use a stale step to communicate the stale input to the next step. We're going to learn that in detail in the later part of this lecture. This is just for motivation. And as a result, we can generate on the right column, the image that is 3 times faster, but the quality is very well maintained. Also, people are interested in image customization, right? Create personalized images based on user-specified input. And, for example, we want to generate something like Song Han riding a horse, but it doesn't look like me riding a horse, right? It's very generic. So we are going to introduce techniques like fast composer, which is from Guangxuan, a training-free method that can blend different people together. Like here, we can have Jensen and Lady Gaga sing together. And this efficient image generation has a lot of applications. This is just to motivate you why we need to learn these techniques. Like on the iPad, we can hand draw a picture, and then after a while, you see it takes several seconds. We want it to be faster and to immediately render a very good-looking image. And we hope such method can run locally on the edge device. Not only image generation, but also 3D generation. That's also a very hot topic and require a lot of compute. So this is diffusion models creating 3D objects from a referenced image. So the first row is the reference image. And the later rows are the generated 3D object based on just one image. And this is using text prompt, using natural language as an input and create the 3D objects. And also video generation, that's adding another degree of freedom. They are pretty big. It's even harder task requiring much larger model size. And this is from last year and this year. Sora is there, so it's pretty exciting. I just give a text prompt, a stylish woman walking down the Tokyo street, and then it's generating high resolution photorealistic videos from natural language description. But again, this is consuming a huge amount of compute. And we are going to learn techniques to bring down such computation. And so far, we talk a lot about 2D vision, right? But in reality, 3D vision is also very exciting. Like autonomous driving, self-driving cars, they have not only camera sensors, but also LiDAR sensors that collect those point cloud and to understand this 3D world. Unfortunately, that requires a lot of compute. Here is showing the whole trunk of workstation in the back of the seat. You don't want that to hit the whole car. It's very uncomfortable. So we want to make self-driving more efficient to fit everything in a smaller GPU. So this is what we did. Fast LiDAR net to accelerate 3D perception with algorithm and system co-design. Previously, it runs only 5 frames per second. After the optimizations, we are going to learn in this lecture about 3D point cloud acceleration. It can run 47 frames per second. And this is another project we are going to introduce from Zhijian from our group. He's now going to be a assistant professor at UCSD very soon. So this project is called BEV Fusion that combine not only just one sensor, but also combining multiple sensors very efficiently. Here we are showing 6 cameras in the front, in the back, front left, front right, 6 cameras, and also 1 LiDAR sensor on the top. And we want to combine these features to fuse multiple sensors to do the segmentation and also detection. Detection means finding the bounding box, 3D bounding box of the cars, the pedestrians, and everything. And on the right-hand side is showing the BEV map segmentation. BEV means the bird eye view. There's no map. It's completely mapless. In the new city, you can run such algorithms to find the lanes, find the drivable area, find the pedestrian walkway, etc. And on the top right corner is showing that this algorithm is runnable on a JSON Orin, which is a mobile GPU for self-driving tasks. Okay, so that is the first part about the amazing progress of computer vision and the implication for computing, right? Why do we need efficient computing? And these applications, although amazing, they come at a high cost of computational resource. And now let's switch gear to the second part and talk about the advancement of natural language processing. So this is the second year when after ChatGPT, it is very computationally heavy. Actually, when ChatGPT just came to the world, usually it's at a capacity and prevent user from have a cap of 50 messages every 3 hours, etc. We are experiencing exceptionally high demand. Please hang tight, and we work scaling our systems. Those are the bottlenecks. But they're really helping us. For example, Copilot can make very meaningful coding suggestions based on the context. We just give it some prompt, some comment, and then it's going to automatically generate the code very quickly. And also neural machine translation to bridge the language barrier using NLP techniques. So we're going to introduce technique to bring down the model size and also maintain the blue score, which is the quality. So here we are reducing the model size from 176 megabytes to only 9 megabytes. If it is only like 9 megabytes, it's very easy to fit on your phone. And recently, with the advancement of large language model, new capabilities begins to emerge. For example, zero-shot learning and also few-shot learning. So what is zero-shot learning? The model can predict the answer given only a description of the task. There's no gradient, there's no training. Given a new task, you just tell it what is the task, and then it's going to give you the answer. Say, translate from English to French. We are not training a separate model for English to French or English to Chinese, just the same model using different prompt to describe the task. And zero shot means there's no example and directly translate from cheese to French, right? And also the large language model have the capability called few shot learning. So we just see a few examples, we just feed it with a few examples of the task as part of the prompt engineering. Say translate to English to French, and then we are going to give it 3 examples, and then finally give the result to translate cheese, right? So again, there's no gradient, there's no fine tuning. I just design the prompt smartly. The model is capable of doing such zero shot or few shot learning. This seems very exciting capability. However, like we can expect, this comes at a very high cost. So this is the few shot, 1 shot or 0 shot learning accuracy. So to achieve higher accuracy, the model size has to grow very fast, from 13B to 175 billion parameter. Every small percentage of accuracy improvement comes at a high cost of much larger model size and requiring more GPU resources to serve such models. You see that the curve is very flat, means every small percentage of accuracy improvement comes at a very high cost. Large language model also have another very interesting emergent capability, which is called a chain of thought. So let's see, what is chain of thought? Standard prompting, say Roger have 5 tennis balls. He buys 2 more cans of tennis balls. Each can has 3 tennis balls. How many does he have? It's 11. Since 5 times plus 3 times 3, 2 times 3, that's 11. And then if we ask another question, given the same prompt, the cafeteria has 23 apples. If they use a 20 to make lunch and bought 6 more, how many apples do they have? What should be the correct answer? 9, right? But the answer at that moment given by ChatGPT is 27. Obviously, that's wrong, right? What if we prompt it in another way? Say, Roger, given the same question of Q1, the answer in blue showing Roger started with 5 balls, 2 cans of 3 tennis balls, 3 tennis balls each is 6 tennis balls, and 5 plus 6 equals to 11. It describes the entire thinking process, how the answer 11 is arrived. Prompting this way to show not only the result, but also the chain of thought thinking process. And given another Apple question, the model can output a new answer. Here, cafeteria had 23 apples originally. They used 20 to make lunch. So they had 23 minus 20, that's 3. Okay, step by step, thinking step by step. And then they bought 6 more apples. So they now have 3 plus 6, that's equal to 9. The answer is 9. Now we can understand it correctly. So we are going to introduce some of such prompt engineering techniques so that it will be very practical. You can interact with these large language models more effectively. Again, such accuracy comes at a cost of very high computational cost. So this is the accuracy with the GSM 8K middle school math word problems. And then versus the x-axis is the model size. In order to achieve high accuracy, the model has to be pretty big, like 175 billion parameters or 500, even half a trillion parameter, which is leading to the figure we showed initially. The model is growing much faster than the hardware. And on the right-hand side is a server in the basement from our lab to train these models. We actually purchased it about two and a half years ago. At that time, we have 200 gigabit InfiniBand, but the moment we purchased it, the moment it becomes outdated. Last year, when I gave the lecture, the SOTA was state of the art was 400. Now it's 800. So this area is just moving so fast. So it's very timely to learn these techniques to catch up the wave. We also designed a couple of techniques to reduce the computation and by finding the redundancy in natural languages. Actually, in natural language, there's a lot of redundancy. Say, given the sentence as a visual treat, the film is almost perfect. That's the example on the left. We can trim it. The task is to classify the sentiment. So we can trim the sentence to be as treat, film perfect, or even trim it to film perfect. They can still classify this is positive, this is positive sentiment. So showing that human language has a lot of redundancy, we can take advantage of that redundancy and do a sparse attention. So this is a project we did about 4 years ago, called a sparse attention. We can actually remove those redundant tokens that doesn't heavily attend to other tokens. Like in this example, I bet the video game is a lot more fun than the film. Video attend very heavily to game, but the word I and the doesn't attend to any words very heavily, so we can safely remove those tokens. So those are some of the technique we are going to dive deeper in later part of this lecture. Today, we are just giving overview for you to get a taste of what we are going to learn. Okay, so these large language models are pretty exciting. How can we deploy them on the edge? Deploying large language model on the edge would be super useful. We can run Copilot services like code completion, like Office or game chat, everything locally on the laptops, in the cars, in the robots. We don't have to worry about latency, networking, Wi-Fi, or sending our private data to the cloud, right? So deploying this large language model locally on the edge is super demanding. And in this class, we have two labs actually dedicated to how to deploy a large language model locally on the edge by using large language model quantization techniques so that you can run a 7 billion parameter or even 13 billion parameter model locally on your laptop. So this is a demo showing, this is a pretty outdated MacBook. It's only MacBook with an M1 chip, not even M3 chip, but still it can run reasonably fast to write a C code given the prompt to sort an array. And we are going to introduce techniques to quantize these large language models from 16-bit to only 4-bit. Okay, gradually from 16-bit to 8-bit using smooth quant, and to even 4-bit using AWQ, activation aware weight only quantization. Actually, the smooth quant paper actually comes from this lecture 2 years ago as one of the course project with Guangxuan. So maybe this year, some of you may come up with even more exciting projects that may lead to even a publication in the future. And the key idea is that we find lots of outliers, very big values on the top right corner in the activations, and we want to make it smooth. Since matrix multiplication is linear, we can scale the weight and gradient so that they can be equalized and smoothed, such that it'll be much easier to quantize and utilize the full dynamic range. We are going to implement such algorithm in lab 4. And also we are going to introduce the inference library, an efficient inference library in lab 5, so that you can implement both the algorithm, the quantization algorithm, and also the inference library on your own, which actually require pretty deep understanding of how computer systems work. You must be able to write a C program, not just Python, but low-level C program, very comfortably, manipulating pointers, single instruction, multiple data, familiar with cache, how cache works, what is locality, what is multi-threading. We are going to implement those techniques using multi-core processors, using CMD techniques, and also register level parallelism. So that's why we enforce these prerequisites so that you can complete the labs. So here we have a demo called TinyChat, which is a fast inference library by Haotian Shang. We can deploy a large language model, 7 billion parameter large language model on a Jensen Ori Nano, which is a very small mobile GPU. We 3D printed this TinyChat computer to interact with the input in real time. And this is showing we can actually run large language models on resource-constrained edge GPU. So this is a Jensen Ori. We can use TinyChat to run large language model on this Jensen Ori very smoothly. Even 13 billion parameter model. And this is comparing with quantization and without quantization. It'll be much faster if you can use the activation aware quantization, the AWQ. So on the left-hand side is showing running this large language model without quantization is slow. And on the right is showing with the 4-bit quantization is faster from 50 tokens per second all the way to 166 tokens per second. And running large language model on the edge device can have a lot of applications. So for example, Apple Intelligence here can do summarization to summarize some of your emails, smart reply for emails, and also writing tools to help you correct the sentiment to make it more professional, etc. So far we talk about vision, language, and now let's jump into multi-models. So what is multi-model? So we combine image, language, audio, action, different modalities project them into the same space and understand and process all these different modalities of input and output different modalities. Can we take image, language, audio, video, action in, and then output potentially not only text, but also image, video, even actions? Okay, so that's a multi-model problem. And the challenge here is to how do we align the representation, the embedding from different input modalities. So one example is this work called Lava, who can understand the images and take language prompt with the input image and output the description in language. So here, do you know who drew this painting? And Lava is going to say the details about this Mona Lisa. And here is showing with quantization techniques, we can also quantize them to only 4-bit without losing accuracy. Like in this example, this is the input image and some text description together with that. With naive round to nearest quantization, it's going to say something weird, like there are small pictures of the Earth and other planets placed on top of the food. But with AWQ quantization, it says the meme in the image is a lighthearted and humorous take on the concept of looking at pictures of the Earth from the space, right? So with proper quantization techniques, we can not only accelerate the large language models, but also the visual language models. Later, we designed this VLA, the visual language model. We are also going to cover how do we train and run inference on visual language models. So the key idea is to produce the visual tokens. Okay, so not only language can be tokenized, images can also be tokenized. And how do we tokenize images is by using the visual transformers. We're going to have a dedicated lecture just to introduce what is a visual transformer and also how do we design efficient vision transformers. So with a vision transformer, we can project the input image into several tokens and concatenate the image token with the text token. So basically, we can expand this idea to other modalities as well. So people are realizing everything can be tokenized. Everything is token in, token out. And we find in this in this lecture, we are going to learn those training recipes, like data and training recipe actually matters more than the architecture itself, and why visual instruction tuning is not enough, and why we need visual language pre-training, and why image text pair is not enough, but we need to have interleaved image and text, and how do we blend them? How do we set the proportion of how much of each? And we are also going to talk about visual in context learning, which is pretty exciting capability. And how do we expand it from images to videos, which require much longer context length, since each frame will take about 200 tokens. If you have an hourly long video, you want to understand like a film that require very long context. So in this lecture, we are going to introduce long context techniques. How do we handle the linearly growing memory, if naive, rather than naively using the linearly growing KV cache. So here are some of the capabilities modern visual language models such as VLA can achieve. Given this video, please tell me what happens in the video. And VLA can say, the video shows a soccer game where a player scores a goal and the crowd cheers as the player celebrates it with his teammates. Okay. So we have a demo link here at vla.mit.edu, free to play with it. Given this video, according to the video, what will happen, likely to happen next, Vila says the video shows a blender with strawberries inside, and it's likely that the blender will be turned on to blend the strawberries into a smoothie. So it has the word knowledge, knowing that given such a few frames, what's going to happen in the next. That's also called a word model. Okay, word model with the word knowledge, understand how the world works, given some frames predict what's going to happen next. Similarly, in this case, what will likely happen next? Vila says the next step in the video is likely involve the person grinding the spices in the mortar. A very interesting capability is the visual in-context learning. Okay, so what is in-context learning? We're not telling what is the task, but we're just showing some examples. So here the prompt is image Boston, image Toronto, and image, and it's going to say San Francisco. Right? We're not explicitly telling that, please tell me what is the city in this image, but we're just showing some of the examples. And then the model is going to understand, okay, the task is to tell the user where is the city. Okay, so that is enabled by using the interleaved image text training. So data blending, this training recipe matters a lot in the area of large language models. And we are going to introduce visual language model in this lecture. Okay, next one about word knowledge. So anybody can guess where is this? Given this picture.
Okay.
Oh, very nice, very nice. Spongpay, right? It required word knowledge. You have seen lots of places to understand that, but true individual language model can also tell where a specific image is. Actually, when I was traveling in Europe earlier this year, I took a random picture, and to my surprise, it can tell me this is actually a particular place described very accurately. So I was quite amazed by the word knowledge it may have. So feel free to play with it or even implement it in one of your homework. We're also going to learn this technique. Can we bring this large language model, vision language model, locally to our laptops, right? So that we can play with it, interact with it, have full control with it, compress all the word knowledge into a laptop. So here is what we can do. For example, we can describe the painting in details. It's running locally on a laptop. So in lab 5, we are implementing a language model alone. So we can also implement the visual language model as extra bonus, extra credits. So feel free to talk to me if you want to do the visual language model for lab 5, something like this demo. Okay, so another modality would be the action, right? We can use the visual language model also to output other modalities like actions, right? So here the instruction is bring me the rice chips from the jar, okay? And the current step is opening the jar. It helps do the planning. Since using the large language model contains a lot of word model, it understands in order to bring the chip, you first need to open the jar and then take the rice chip out of the jar and then place it, and then close the jar, etc. Right? But unfortunately, this is accelerated by 4x speed, right? It runs only 3 hertz due to the high computational cost and networking latency, because the images are transmitted over the internet to a workstation and then transmitted back the final result. Okay, so this is the RT1 from Google is also already pretty amazing, but highlights how important it is to learn these efficient deep learning computing techniques like in this lecture. Similarly, deep learning for games, AlphaGo beating LiSouDou is taking 1,920 CPUs and 280 GPUs, $3,000 electric bill per game. That's super expensive. Or the AlphaFold require 16 TPU v3s, which is 128 TPU v3 cores, trained for a few weeks. So all these amazing capabilities comes at a high cost. Okay, so let's switch gear from visual language to multimodality. Now we talk about these 3 pillars: algorithm, hardware, and data. In particular, we want to highlight the advancement of hardware that is the driving force for this Cambrican of efficient deep learning computing. So this lecture, we are going to introduce some of the hardware and system techniques as well. And the philosophy is that we want to do the whole full stack design, okay, on the software part, full stack design from the algorithm part, the demand of computing, to the system part, which is the supply of computing. We want to close the gap by reducing the demand and increasing the supply. Okay. So the recent trend of modern hardware design is that the microprocessor frequency is plateaued. The single core performance also plateaued. Moore's law is scaling down, but the number of cores is increasing, and the number of transistors is also increasing. So parallel computing, specialized computing is the new trend in this context. And also precision matters. The communities keep advancing the low precision arithmetic from floating point 32, floating point 16 to integer 8, 8-bit integer to FP8, 8-bit floating point, and also even to FP4, 4-bit floating point, which is to appear in the latest Blackwell NVIDIA GPUs, right? So the precision is keep decreasing. In this lecture, we are going to learn all the details about what is a floating point, what is FP8, what is E5 M2, okay, what is the mantissa. So what is FP4, why Blackwell is so amazing, it can have such high peak performance in the quantization part of this lecture. And on the right-hand side is showing the single chip inference performance 300 times in 8 years. This is from the slide from my PhD advisor, Professor Bill Daly. Is showing that from scalar FP32 to FP16 to HMMA tensor core in V100, the int8 TOPS increased to 125, and again it doubled by using int8 IMMA tensor cores to using structure sparsity 2 to 4 sparsity in A100, like 300 performance improvement in 8 years. That's like pretty amazing improvement. And in this along this line of innovation, software is actually playing a very critical role in especially the advanced technology node. So this is from 65 nanometer, 28 nanometer, 7 nanometer, 5 nanometer. You can see the purple part, which is the software component, is getting a very big chunk of the total advanced design cost. And that's always also creating the moat for a good silicon to be able to attract a lot of good customers. It has to be programmable, has to be easy to use, especially the large language model, this generative AI. The models are changing, iterating very fast, changing every day. How to make it flexible is super important. So in this lecture, we have a lot of focus on the software part of efficient deep learning computing. We don't design new hardware in this lecture, but how to utilize existing hardware and what is the implication to design new hardware. So here we show from 2016 to 2024 the advancement of GPUs. We put them into 4 different benchmarks. The dense FP16 performance measured in tera operations per second. We're going to learn in the next lecture what is TOPS per second, what does it mean? What is dense, what is sparse, what is FP16. So we're going to learn dense and sparse in the pruning lecture from next Thursday. And we are going to learn quantization precision a week after. So from P100 to B100 is actually 100 times, 100 times more TOPS per second. In particular, from H100 to B100, it even doubled the TOPS per second, which is super amazing. And even didn't consider the FP4. If we add FP4, it will be way higher in this chart because it's showing just FP16. And here is the memory bandwidth. Computation is cheap. Memory is super expensive. From A100 to H100, it almost doubled, and then more than doubled from H100 to B100 with respect to the memory bandwidth. And we are going to introduce these concepts like why data movement is expensive, why energy is dominated by moving data. And here is showing the power. Unfortunately, the power is also growing pretty fast from A100 400 watts to 700 watts in H100 and B100. If you have 8 GPUs in a node, you can calculate how much power you have. So 8 nodes, all the GPUs will take maybe 4,000, 5,000 watts, and altogether the whole node will have 10,000 watts. You have to prepare 10,000 watts just for a single node. And as a result, the space will not be the constraint, but the power supply, the energy, the cooling is the new bottleneck. Previously, when we are having the A6000 GPUs, so we can have two cables serve the entire rack, but now 2 cables can only serve 4 nodes of A100 and only 2 nodes of H100. So power efficiency is super important. And in this lecture, later part of this lecture, we are going to organize a lab tour. So we'll show you down to the basement to our server so that you can see how these models are trained, what is like a mini data center, what does it look like? What is the cold aisle, hot aisle, the rack, the switch, InfiniBand, the cables, and the modern GPU, what does it look like? And next is the memory. So unfortunately, memory is growing at a slower speed compared with compute. Currently what we have in our lab is 80 gigabyte A100 GPUs. H100 pretty much stays the same, and B100 give a pretty exciting leap to almost 192 gigabytes. So this is for the cloud, for training and serving. So let's also look at the edge. For example, on the phone, we want to have those low power chips. Like here is only 10 watts, 10 watts S855 all the way to S8 Gen 1. S8 Gen 2 is also there, but we didn't find the public numbers, so we didn't put it there. The performance is also increasing pretty fast, like a couple of, like almost like half a hundred, like 50 TOPS per second, and the memory is roughly 816 gigabytes for Qualcomm DSP. Apple also offers this Apple Neural Engine, energy efficient and high throughput for machine learning applications. Similarly, with the Qualcomm DSP, it's 35 TOPS per second. However, we should not just look at the peak performance, like 35 or 52. Can you make a conclusion that Apple or Qualcomm, which one is faster? Actually cannot, because it's a multiple dimension. The peak performance doesn't directly translate to measured speed. There's so many factors we're going to learn in this lecture, like the activation, data movement, weight, data movement, memory bandwidth, utilization, all matters a lot. And also there's the mobile GPU. People very widely use in the cars. For example, this is the Jetson Ori, which is used in many EVs, delivers a couple of hundred TOPS per second, consume about 60 watts, 64 gigabytes of memory. And there's going to be a new Thor coming up, which is the next generation of AJX Ori. And also there's microcontrollers for many IoT devices, like the smart home camera might have one of these small devices, ARM devices, just a couple of 100 milliwatts, but the memory is also super small, just a few hundred kilobytes of SRAM, maybe a few megabytes of maybe DRAM or even no DRAM. Some microcontrollers has completely no DRAM. We have to manage the memory super carefully. So from cloud AI to mobile AI to tiny AI, there's actually a big gap between the amount of memory that you have, tens of gigabytes versus a couple of hundred kilobytes. So edge AI device still have a huge gap to cloud processors. And what we learn in this lecture is going to try to close the gap by using smaller models. Okay, so those are the three pillars: the hardware, data, and the algorithm. And our goal is, rather than using a lot of compute, emitting a lot of carbon, using many engineers, train a lot of data, TinyML's goal will be how to use less computation, less carbon, fewer engineers, automated, train on less data. So this is the course overview. Let me use the remaining 10 minutes to cover some of the logistics. So the lecture is every Tuesday and Thursday from 3:35 to 4:55 in this classroom. And we will record the classes. The office hour will be directly after this lecture on every Thursday from 5 to 6 p.m. The room number is 38344. That's where our office is located at. Feel free to ask questions during the office hour or go to the Piazza. Make sure you sign up on Piazza. And also we use Canvas, like other classes, to submit the homework. And you can email us at efficientml-staff@mit.edu if you have any external inquiries. We're also going to create a mailing list. You just make sure you take care of the mailing list, so everybody is welcome to join that mailing list so that we can broadcast some of the news, project ideas. Some company even want to have those internship openings or full-time job openings. We can disseminate through that mailing list. So stay tuned. Eugene will send a notification for the mailing list sign up. And the prerequisites. So this year we enforce two prerequisites. One is the 6191, which is computation structures, since the lab 5 and lab 4 require a deep understanding of how computer systems work, like what is cache, what is locality, what is parallelism, 5-stage pipeline, page table. Since we're going to talk about the page attention, speculation, we're going to talk about speculative decoding. And most importantly, you have to be comfortable with how to write C programs. Since the lab will be written in C program, and also multi-threading techniques. The second prerequisite is 6.390, the introduction to machine learning class. Make sure you are familiar with how to use PyTorch, since all the labs will be using PyTorch. So we are going to cover roughly 3 sections. First section is about efficient inference technique with pruning, reducing the number of parameters, quantization, reducing the precision for each parameter, and also neural architecture search. How do we design an efficient neural network architecture? And also distillation, how to use a teacher model to distill a smaller model. We're also going to talk about efficient training technique, how to do gradient compression on device training, and also federated learning and parallelization, including data parallel, model parallel, pipeline parallel, and also sequence parallel for large language model. We're also going to introduce application-specific optimizations. The most important one, of course, is transformers and large language models. We're going to introduce the entire architecture, how transformer work from the position encoding all the way to what is QKV, what is attention, what is different context extension techniques, what is rope, etc. We're also going to introduce diffusion models, how diffusion model works, video understanding, point cloud understanding, etc. So a key concept is system on algorithm co-design, which is covering actually combining a lot of knowledge we learn from the EE side, the CS side, and also the AI plus D side. So hopefully it'll be a class you can take in later year of your undergrad, or maybe in the first couple of years of your PhD to do such interdisciplinary research. So on the EE side, the 6191 or microcomputer project lab, hardware architecture for deep learning, those are very related classes. CS side, computer architecture, software performance engineering, mobile sensor computing. AI plus D side, intro to machine learning, deep learning, advances in computer vision, natural language processing are all related classes. We will have 5 labs over the course of the semester. We are going to use Google Colab for the first 4 labs, so you don't have to worry about the hardware. First one is about pruning, second one about quantization, third one is about neural architecture search, fourth is about large language model compression, and the 5th one does require hardware, which is a laptop. Hopefully you all have a laptop that is more than 8 GB of memory. Make sure you have more than 8 GB of memory, and available storage should be at least 5 gigabytes. So unfortunately, we don't have the budget to buy everyone a laptop, but I'm assuming everyone already have a laptop, either x86 or ARM, either Mac, Linux, or Windows. We have carefully debugged so that it can fit across different platforms. And Jerkai will be the TA if you have any questions related to Lab 5 and hardware. So grading, we will have 5 labs. Each one is 15%, followed by a final project. 25% is open-ended, but we'll give you some project ideas to start with. It is done in a group of 3 to 4 students, consisting of a proposal, a presentation, a poster presentation, and also a final report, just 20%. We also give 44% for participation bonus. And all the assignments are due on 11:59 p.m. on the due date. And the late policy is that we have 6 total late days without penalty for the entire semester. given the large number of enrollment, we don't have any exception for the 6 late days. And a lot of days are counted by day. Each new day will, the penalty will be 20%, 50%. So homework is worth 0 credit 2 days later. So prerequisite, this is quite important. So students who don't fulfill the prerequisite will be deregistered in the 2nd week of the class. So if you believe you have equivalent prior experience, including both computer architecture and also the machine learning, please make sure to send us the petition on this form. Make sure you take a photo of this form if you don't meet the prerequisites to submit your petition form by this Friday, 11:49 p.m. Okay, and then our TA will review these petitions, and student who doesn't fulfill the prerequisite will be deregistered next week. Okay, so these are the 5 labs, and also together with the final projects we did last year, it's pretty exciting. So hopefully you can learn a lot about this amazing efficient deep learning techniques, and we'll see you next Tuesday.